Now I will introduce a solution that achieved fourth place. First, I would like to express my gratitude for hosting this excellent competition. I learned a great deal through this competition and I'm truly thankful. Now let's move on to the solution introduction. Here is the agenda. I will skip the background and focus on presenting the summary and the solution. I will explain summary of our team solution. Approach to the competition. The test set for this competition was anticipated to contain numerous misconceptions not present in the training set. Therefore, enhancing the scores for these unseen misconceptions was a key priority. Next, I'll explain the overall solution. Our scores were private score was 0.60044 and public score was 0.65531. We implemented 5 key steps: data generation, misconception generation, retrieval, rerank, and post-process. I will walk you through the details of these steps shortly. Next, I will explain the details of the solution. First, I will explain validation strategy. We used group k-sort with question ID as the grouping parameter, and the number of faults was set to 5. In addition to checking the overall fault scores, we also evaluated scores on validation data specifically extracted for misconceptions not included in the training data, simulating conditions similar to the test data.
About data generation, we generated pairs of questions and incorrect answers corresponding to misconceptions that appear only in test dataset and do not appear in training dataset. And we use QN72 billion model for data generation. And for each misconception, we sampled 100 examples from train.csv and included in the prompt for data generation. And we generated 10,000 pairs of questions and incorrect answers. Next page, please.
Next, I will explain misconception generation. Our team used QN 2.5 32 billion instruct AWQ to directly generate misconceptions from question text, answer text, and other related data. The generated misconceptions were used as input for the subsequent retrieval model. Initially, we planned to use a smaller model for retrieval, and we expected that utilizing the output from a larger model would enhance retrieval accuracy. For example, when using Salesforce SFR embedding to R, we observed the improvement of 0.01 in top 25 recall accuracy. Since this approach proved effective with Salesforce SFR embedding to R, we applied the same method to the larger models, such as the 14 billion and 30 billion models that were ultimately used. Next, I will explain the retrieval process, focusing on the submission approach. The retrieval models were evaluated using both MAP25 and recall metrics to ensure robust assessment. For the final submission, we ensembled the following models: QN 2.5 14 billion instruct using all 5 faults, QN 2.5 32 billion instruct using only 2 faults due to the inference time constraint. Next, I will explain the training methods for QN 2.5 14 billion instruct. Misconceptions generated during the misconception generation step were added to the text of the question. The loss function used was multiple negative ranking loss, and the fine-tuning was performed using QLoRa. Next, I will explain the key points that were important during training. Increasing the number of negatives was a critical factor. In the final setup, each batch included one positive sample and 47 negative samples for each question-answer pair, with 6 question-answer pairs per batch. Increasing the number of negatives from 15 to 47 improved the top 25 record by approximately 0.015. Another important point was restricting the negatives used for training to those associated with positive samples with the training data. Using negative from all misconceptions resulted in 0.01 degradation in record performance. The scores for Q2.514 billion instruct were as follows. These were the result evaluated across all 5 folds. MAP 25 was 0.511. Top 25 record was 0.923.
The validation score of 32 billion model is as shown in this slide, and it seems the validation score is better with larger model. Next page, please.
Next, the inference process for submission. The ensemble was performed by concatenating embeddings from Q2.514 billion instruct by folds and Q2.532 billion instruct to folds. Inference for Q2.532 billion instruct used VLLM to reduce inference time. Retrieved 25 items from all misconceptions and 10 items from misconceptions not present in the training data. This approach prioritized misconceptions not in the training data because most tested misconceptions were predicted to be absent from the training data. Public score improved by 0.01 during the completion using this method, so it was applied to the final submission. Duplicates were removed afterward. Next, I will explain the retrieval process for generating candidates used in training the rerank model. Candidates for reranking were selected based on an ensemble of the following models: Salesforce SFR embedding 2R, BG large and B1.5, GTE large and B1.5. The MAP 25 and top 25 record scores for these models were lower compared to the models used for submission, with scores of 0.461 and 0.881 respectively. However, during the competition, the rerank model trained with candidates from these models achieved a higher public score. Therefore, we continued using these candidates until the end. Next, I will explain the rerank process. Our team performed inference for reranking on the test set using 3 models. Next, I will explain 2 of the 3 reranking models. For both models, 4 out of 5 folds were trained using QLoRa. The final models were created by ensembling the LoRa components as follows: Model 1 combined for 1 and for 2. Model 2 combined for 3 and for 4. The training used the Q2.532 billion instruct GPT-Q-int4 model and adapted a pairwise approach. This approach predicted whether a question and a single misconception were linked in a one-to-one correspondence. Next, I will explain the key points for training. Similar to retrieval, it was important to limit negatives to those associated with positives. This approach improved the score, especially for data where the target misconceptions were not present in the training data, resulting in a 0.05 improvement in MAP 25. It also improved both the public score and the private score by approximately 0.025. Increasing the number of negatives was another important factor. During training, a ratio of 1 positive to 9 negatives was used, compared to using 4 negatives. This setup improved MAP25 by approximately 0.02 in local evaluation. Also, increasing the number of negatives further improved MAP25 locally. It did not improve the public score. As a result, the number of negatives was kept at 9 to balance performance and training time. Next, I will explain the local evaluation score. The score is based on fold 1. MAP25 for fold 1 was 0.653. For data where the target misconceptions were not present in the training data, the MAP25 was 0.601.
I will explain about Model 3. About Model 3, the weight of model used in the final submission is a ensemble of Fold 1 and Fold 2. And the training method is almost same as Model 1 and Model 2, but the dataset used in training is different. In addition to the competition dataset, we use 2,500 generated samples for training. Next page, please. The validation score of Model 3 is as shown in this slide. We can see that generated data help to improve validation score. Next page, please.
Next, I will explain the post-processing step. The prediction results for misconceptions linked to trained data were multiplied by 0.4. This adjustment was made because many misconceptions in the test set were expected not to be present in the train set. Lowering the rank of misconceptions present in the trained data was expected to improve the test accuracy. As a result, the public score improved by approximately 0.025, and the private score improved by approximately 0.020. The coefficient was determined based on the public score. This concludes my presentation. Thank you for your attention.